Okay, my name is Salvatore Foti. I come from Italy. I am assistant professor of the University of Messina, Sicily. Today, I'm the title of yes, thank you, Mr. Chairman. The title of my presentation is a comparative assessment of the efficiency of conventional and multilevel power converters. This is the outline. First, I will talk about multilevel converters, and then I will show you the asymmetrical hybrid multilevel converter under investigation. In particular, I will show you the comparison of the efficiency, and finally, we have the conclusions. Multilevel converters are used for high power, medium voltage application, for example, electropropulsion system, wind, photovoltaic generators. And they permit to overcome some limitation of a conventional two-level converters. In fact, multi-level converters filters are a high number of output voltage level, low switching frequency, high efficiency, low dependency voltage stress on each power devices, and is also a better power quality in terms of lower total harmonic distortion. A special kind of multilevel converter is now as asymmetrical hybrid multilevel converter that has been proposed in 2015. It consists of an open and winding machine that can be motor or also transformer that is fed from both end sides of each windings. In particular, from one side is connected to a conventional multilevel converter, for example, neutral point clamped type flame capacitor. And on the other side, a conventional two-level converter. The main feature of this system is that it is asymmetrical and hybrid, because the main multilevel converter works at a high voltage but a low frequency in order to eliminate to reduce switching frequency. While on the other side, the two-level converter which works at low voltage but high switching frequency in order to and works as active power filter in order to eliminate all low order harmonics generated by the first converter. In this table, we can see the comparison between the proposed asymmetric high multilevel converter with conventional. In particular, we note that with the proposed reconfiguration, we obtain a high number of output voltage level by using a less number of power devices compared to conventional converters, neutral point clamp and flame capacitor. About the hybrid modulation, low frequency modulation is exploited in multilevel converter, and we can consider a schema select harmonic elimination, in particular a step modulation. In this picture, we can see the waveform of the step of the output voltage, a step waveform. And it's possible to eliminate a set of harmonics. But in this case, the maximum number of harmonics that can be eliminated depends on the number of output levels. In fact, the other harmonics will be eliminated by means the two-level converters. And the worst case, that is the asymmetric high multilevel under investigation, the worst case is when the main multilevel converter is at three-level, because in this case, in case of three-level, we have only one switch angle that is used only to regulate the fundamental component. So it is not possible to eliminate the other harmonics. For this reason, the TLE, the use of the TLE becomes very crucial in this case, because if we set the reference voltage of the active power filter as the difference between the waveform, the step waveform minus the fundamental components, it's possible to eliminate harmonics on the phase voltage of the machine. But the value of the DC link of the two-level converter or of the active power filter depends on the modulation index of the main multilevel converters, because when we change the modulation index, change also the harmonic spectrum. But we can see that in case of n equal to 3, in three-level in this case, we need a DC link of 0.5 VDC1 to eliminate all low order harmonics. In this slide, I want to show you only some experimental tests on a 3 kilowatt induction motor, but only to show you the output voltage waveform. In the left, we can see the case of step modulation with the wave-connected load, and the current is very distortion in this case because we have waveform, step waveform. In the middle, we have the proposed 3-lever plus TLAE, and on the right, we can see the case of 5-lever PWM modulation with wave-connected load. We can see that in the middle, the proposed configuration, with the proposed configuration, we achieve a lower value of total monetary distortion by using a less number of power switches compared to the 5-level PWM modulated inverter. In this paper, a comparison of the efficiency between the asymmetric high multilevel converter, 2-level converter, and 3-level T-type converter has been performed. In particular, we regard the modulation, PWM and step modulation for a 3-level T-type in wave-connected load, PWM modulation for 2-level, and hybrid modulation for asymmetrical. We consider also switching losses and conduction losses for both power switches and power diodes. This is the PSIM model of the IGBT. We are considering diode losses, conduction losses, switching losses. This is also the DQ model of the permanent magnet single motor because we we evaluate the efficiency versus motor speed and current and motor current. So if we see these preliminary results about the efficiency versus speed and versus current, we note that the asymmetric high multilevel converter features flatter efficiency diagram compared to the other 3-level T-type and 2-level T-type. This is an important result because this means that I can have high efficiency for both high speed, low speed, high load, and wave load. For example, in electric vehicles, when the vehicles runs at a low speed, it's possible to have high efficiency. Or also, for example, photovoltaic. For photovoltaic application, during the dark or during the evening, when the output voltage and so the modulation index is lower, we can have high efficiency. But which is the cause of this behavior? If we consider 3-level in wave connected, and in two cases, step modulation and the PWM modulation, we know that we have the same trend, a flatter, when we consider step modulation, because if we consider in the middle a separate power losses, we know that while the conduction losses increases, the diode losses decreases. This means that the efficiency remains about constant flatter. And this, in the right, we can see instead the case of PWM, and the behavior is different from the middle. The same occurs in the 3-level T-type on the right, in case of asymmetric high multilevel converter. About the 2-level, the trend of power losses of the 2-level converter is about constant because it works at almost unitary modulation index, as shown in the figure on the right. So since the trend in case of PWM depends on the modulation, the trend of the efficiency depends on the modulation index. The modulation index is almost constant. In this case, the 2-level converter doesn't involve problems about efficiency. In conclusion, I investigated the reason why the asymmetrical multilevel converter has a flatter efficiency diagram compared to 2-level converter, 3-level converter. And from these preliminary results, because these are preliminary results, seems that the flatter efficiency trend is mainly due to the step modulation. This is important because it's possible to detect the most suitable inverted topology for application, for example, electric vehicle, variable speed induction motor drive, wind turbine, where it is required to achieve high efficiency for extended speed of power and so on. About the next work, I will investigate what happened when I replace another topology of main multilevel converter, for example, neutral point clamp, And I will also perform experimental test in order to verify if this model is correct. Okay, thank you.
Right, thank you for the presentation. So, any questions from the audience?
Yes.
Go ahead.
I'm Ildefonso Muñoz from Spanish National Center for Renewable Energy. First of all, thanks for your kind presentation.
Thank you.
I would like to know if there is a study about the efficiency loss due to the temperature in the
Model.
from the
Yeah.
multilevel converters versus
Yes.
conventional.
We used in fact we used the PSIM software. PSIM software permits to simulate a real component by considering also the temperature behavior of the IGBT. In fact, it's possible by PSIM. It's possible to download the LT space model of the IGBT. So it's real. In fact, the next step will be to evaluate experimentally in order to verify the model.
Because from the point of view of the PV plants, PV inverters in plant, it's an important issue because there is a wide range of temperature in its operation. And, the rating effects can be considered. Thank you.
Thank you.